In this video, we're going to introduce the Lorenz Force. So recall that through Coulomb's law, we have an idea of the relationship between the charge and the electric field in terms of the amount of force that the electric field will apply on the charge. Now recall that the basic element of a magnetic field is a moving charge or a current, but in this case, let's call it a moving charge. The purpose of this is the Lorenz force is we talk about the force that a moving charge will have due to a magnetic field. Now the key equation to remember is that the force experienced by a moving charge can be calculated through this relationship, QV cross B. So this equation describes the Lorenz force. Now let's start by qualitatively visualizing this. Let's say that we have a uniform magnetic field that's coming out of the board. So this symbol just represents a uniform field everywhere that's in the direction coming out of this screen. So in this case, we're going to refer to this as a magnetic flux density over here. So remember, B is equal to mu h. And let's bring in a positive charge that's moving in this direction over here. Now the resulting force is the cross product of V and B. So one way to do that is if you have your index finger or all of your non-thumb fingers pointing in the direction of V, and then orient your hand such that when you curl your fingers of your right hand, that they go in the direction of the magnetic field B, or the magnetic flux density. Then the direction that your thumb is pointing is going to be the direction of the force that's experienced. So again, if we call this X and we call this the Y direction, then if you point all of your fingers in the X direction, curl them out of the screen towards the Y direction. If you correctly use your right hand, then you will find that your thumb is going to go in the Z direction over here. So in that case, if you use the right hand rule, you can see that this charge will experience a force that's going in the Z direction or the downward direction over here. So one of the key things that I want you to be able to do after watching this is to know this equation, this F equals QV cross B, and then if you were given a situation to at least know what direction the force is going to be. One important concept that results from this is that magnetic fields do not do work. So magnetic fields are lazy fields. They cause force, but they don't do work. And why is that? Recall that in order to get credit to be doing work, the force has to be its force times distance, right? Or force in the direction that the particle is actually moving. Now the direction that the particle is moving is described by this V vector, right? And when you're taking the cross product, the result is always going to be perpendicular to both of these vectors. So the reason is because F is always going to be perpendicular to V. So a magnetic field induced force will always be perpendicular to the direction that the particle is moving. Therefore, even though the particle experiences some force, it will never end up getting work. It will never perform work. It will never get credit, so to speak, because the minute that it changes direction, the force will also change the direction. And the force, since it's always perpendicular to the direction of the particle, it never gets credit. Now, following a logic flow similar to what we did with Coulomb's law, remember we defined the field, the force that's experienced due to a charged particle and electric field, but then what did we do? We then brought it down to a point form, right, to talk about it in terms of charge densities. So if we take the derivative, if we take the derivative of both sides for two of the variables, namely F and Q, you can rewrite that the force is going to be equal to the charge QV cross B. But in this case, we're talking about infinitesimal charge and an infinitesimal amount of force resulting from that charge. Now let's take a closer look at this. We can rewrite dq, a small section of charge, as equal to the charge volume density times a small volume of charge, right? So plugging that in, we're going to get that a small portion of the force is going to be an infinitesimally small section of the force is going to be, a small amount of charge, which now in this case is rho dv times the velocity cross b. So remember, this is volume charge density. So this is different than this velocity vector here, which we can then move the dv out to say that df is going to be equal to rho v cross b for a small section of volume that you would then integrate. And what's a volume charge density times a velocity? Going back, this is going to be equal to j, right? So now we can rewrite this in terms of different forms of current density that we're used to. So in the form of our regular current density j, we can write that df is going to be equal to j cross b dv. And this is another form of the Lorenz force equation that we'll use a lot, just because this current density j is a commonly defined quantity. Now, if we lump this j together with the volume integral, we can actually rewrite this in a few more different forms, right? A few other forms of current that we have. We can also, from our prior discussions, we can also see that this can be converted in terms of a sheet current density integrated over the surface. And similarly, it can also be I dot dl. So this way, we can also rewrite this in this differential force in terms of the other forms of current that we have. It can also be equal to k cross b surface integral, and also I dl cross b. In this case, it would just be a line integral. So here we have the general form for a single charge, qv cross b, that allows us to calculate the force. But if we want to break it down into an elementary charge or an elementary current component, we also have this in terms of I, so I dl cross b would be df, also sheet current density, and overall regular amps per meter squared current density. We now have the form to figure out what a certain amount of current density in these different number of dimensions contribute to force. And so if you take in particular the IDL part and do a line integral, so integrate across the dl, you get the form that the force is going to be equal to the clothesline integral of IDL cross b, which is, since I is a constant, you can also rewrite this as minus I clothesline integral of b cross dl. And where did this negative sign come from? Right, because I switch these two, right? So when you do a switch in a cross product, you add in a negative sign. So this is another form. So you see that now we have that if you have a current loop, this is a little bit more intuitive, where if you have a current line and you do a clothesline integration, you can then arrive at the total amount of force.